So instead of using a linear structure like this, we're going to use a heap. Okay. The hell's a heap? A heap is a complete self-balancing binary tree where each node meets the heap order property. There's a lot going on here, right? Each aspect of this, let's see, this needs defined, and this needs defined, and this needs defined, and technically binary tree needs defined too. So let's go through this. Complete tree. What's a complete tree? Well, we talked about this in a previous class when we talked about trees. A complete tree is a tree where every level is completely filled in, except for potentially the last level. And if that last level is not completely filled, it's filled from left to right. So this tree that I'm drawing now is always a complete tree because every level except for the bottom level is always completely filled in, and the bottom level is filled in left to right. Hey, it's filled in. Now we go to the left child of the left leaf, and we keep going. Right? This is a complete tree. What about a self-balancing tree? That's not something that we've necessarily run into. So let's just think about what that means. Self-balancing. Balanced. Well, it's probably going to be fairly even. Okay. What's that mean for us? It means that it's going to automatically distribute nodes evenly. And it's going to do that across a level before moving and increasing height. So a decently balanced tree only has leaves on 2 levels. And those levels are adjacent to each other, for lack of a better term. A self-balancing tree does this automatically. So when we look at a tree that is in this format, and I'm just going to arbitrarily draw one here. I'm going to go one more level down, right? And this is not a complete tree. What this means is that if you take a subtree at any level, they're going to be approximately the same size. Well, look, if we grab this subtree and this subtree, they're exactly the same size. If we instead go another level down, now we can grab, well, this is 1, this is 2, this is 2, this is 1. As a percentage, that's a wild swing, but as just counting, that's not bad, right? Now compare that to something like this. This is wildly unbalanced, right? So this is what we're talking about. A balanced tree automatically distribute nodes across the level, which means that subtrees of the same level are going to be about the same size. So we got a red-black tree, right? That's an example. AA trees are a type of red-black, scapegoat trees, and heaps. These are all examples of self-balancing trees. Why is this so crucial? Why am I going on about this? Well, let's think about the equation that we have for the height of any binary tree. Our height is going to be greater than or equal to log base 2 of n plus 1 minus 1. Well, if we can minimize that height, then that means that we can get to any node in the tree by iterating in a path from root to leaf, and we can minimize the calculation. We can guarantee a minimum calculation of big O of h, which is a log process. So if we can keep our tree relatively balanced, we can keep our height minimized and make our processes as fast as possible. Okay. What's the heap order property? This is the thing that you guys are probably thinking in your head, right? Like you guys jumped immediately to what's a heap? Well, you didn't necessarily say heap order property, but you said, well, this, right? The relationship between parent and child nodes throughout the heap, right? The heap order property says that there has to be a relationship. And the heap order property will define what that relationship is. Specifically, we can have a max heap ordering property, which says that the ordering value of the parent is greater than or equal to the ordering value for all of its children. And a min heap says that the ordering value of the parent is less than or equal to the ordering value for all of its children. Notice that for both of these, equal is on the table, which means that you can have a heap full of nothing but equally prioritized stuff. That's totally valid. Okay? We're doing heaps and priority queues. We talked about priority queues. Priority queues want a value, want to get the next thing out with the minimum key value, typically. Well, maybe we should be looking at a min heap where our ordering value is the key. And that's what we're going to do. So now that we've got this completed, we can say, what is a heap? A heap is a complete self-balancing binary tree. Right? Complete meaning every level is full and then it's filled left to right. Self-balancing, which means that a level is filled out before moving on to the next. Binary tree, any node has between 0 and 2 children, where each node meets the heap order property. Okay, so we can have a min heap or a max heap. We are going to be looking at min heaps. That's what we're going to do. Okay, but everything applies the same for a max heap.